You're venturing into chapter 2. So if you've been keeping track, we started chapter 4, then we went to chapter 3, now we're in chapter 1, and now we're finally to chapter 2. And we're going to be discussing the op-amp. This comes with some assumption that you've played with these before. For example, if we hook this up here and we ground that, we'll put a resistor here, and we put an input voltage here, an output voltage here, and we call this RF and R1. If you've never done this before, you need to go back and review op-amps. This is called an inverting, and the V out over V in on this one is going to be minus RF over R1. We've done this before, so we've always treated op-amps prior to that they're ideal. So ideal. What does that mean? And I'm also going to start with my helpful model of what goes on inside of an op-amp. We have a plus side and minus side. Notice I drew it upside down from what I just drew it. Inside here is a flunked out double E student. It's the only job he could get. We shrink him down like in that stupid movie. We put him inside of the electronic circuit. He has a little DMM in which he can see the voltage from here to here and nothing else. That's all he can see. Other than that, he lives in total blackness and darkness. Okay. Over here, with his hand, he has a knob that controls the output voltage. And what he does is when he sees that V+, when he sees that this is positive, he cranks this more positive. When he sees that this voltage difference is more negative, he cranks this more negative. And so if we have 0.1 volts between those two, he's going to crank this knob to the right. In fact, he's going to crank it, and I've been told that his name should be called Soldier Boy. And if you want to refer to him that's what happens. If he sees that this is negative, he's going to crank it in the opposite direction, making the output negative. And he's going to crank it forever until he sees a difference in this. And so if it's set up just like this, and he sees a voltage difference, he's just going to keep on cranking until the op-amp blows up, because this is connected typically to plus 15 and minus 15. He's going to crank it until it hits those rails. So you can try that with an op-amp. Plug it in. Don't connect any feedback from the V out to V in minus, and see what happens. Now, what really happens with that, imagine that our dude is still in there. This is minus, this is plus. And with this resistor coming back here, and we're going to ground this, what he sees from here to here, I'm going to call this Vx. He sees a voltage minus Vx. Why? Because this is 0, and we're going to see negative of whatever. The voltage difference that he sees is V0. And so let's just put in 1 volt here, R1, RF. We put in 1 volt, let's just put in these are both 1 ohms. Okay? And let's just assume at the beginning that this is all 1 volt. And everything here should be 1 volt, because one of the rules of the op-amp is these two currents are 0. Okay? So there can be no current in or out of it. And we're violating the rules a little bit because I'm saying all of these, but I'm saying initially. So Soldier Boy in here is looking at that negative terminal, knows that this one's 0, and sees this and says 1 volt. I'm going to crank my thing negative, because he sees negative 1 volt. He says negative V. He sees negative Vx. So he's going to crank this negative, and so he cranks this down to 0.5. In the meantime, this here was 1. This is 0.5, and these are both 1 ohms. There's no other path for current. This is a voltage divider, so we get 0.75. He says, I'm going to keep on cranking it negative. So he gets down to 0.1. This is still 1 because that's an applied voltage. This is 0.1, and this is going to be halfway in between, which is going to be 0.55. the way I did that, 0.9 difference between, divided by 2, add it to the point 1, so 0.45 plus 0.1. Okay, and then he finally gets to 0, and that's going to be 4.5 volts, and he says it's, or 0.45 volts, and he said, or 0.5 volts, right? And he says that's still, you know, not there, and so he keeps on cranking. He gets to negative 0.5. Now we have a 1.5 volt, and so this is going to be positive 0.25. It's still a positive voltage here, which means he's seeing a negative, so he has to crank down negative even more. And as he's cranking this, finally he gets to 1 volt. Okay, 1 volt, or sorry, minus 1 volt, minus 1 volt, 1 volt. That puts this at 0, and suddenly he lets the hands off because he's gotten that there, and that's how an op-amp works. And it literally cranks. We crank this voltage until these two are the same, and thus we need negative feedback. And the reason why I went through this is because instead of Soldier Boy in there, what we have is, if we remember, we have plus and minus. We're going to say this is Rn. That is, I'm going to call it AV0 times Vn, plus to minus Vn. Rn is equal to infinite, okay? And this is the same thing. This is Soldier Boy. He's going to crank it until the voltage here, either equals or until it saturates. And so the question is, what's A0? And this is going to freak you guys out a little bit maybe. Ideally it's infinite. Now that's not quite true. And in a 741, that's 10 to the 6th. It's a big voltage gain, and this is in units of volts per volt. And I know that you're all thinking, and maybe you're thinking, but that's not true. Because when we did it in lab, we got gains much less, but that's because we had feedback built in. And I'm going to prove this to you right now. So I'm going to draw it without the op-amp. Okay, this is our plus, this is our minus. I'm going to call this Vin. Rn is still going to be infinite. We're going to have this over here. That's our output. This is going to be AV0 times Vn. And that's an op-amp right there. Okay? Just have to draw the triangle. Okay? So what I'm going to do, though, is I'm going to do our classic feedback like we'd want to. I'm going to put V in here. I'm going to call this RF, and against better judgment, I'm going to call this R1 versus Rn. I don't want those to be the same. I'm going to ground that point, okay? And I'm going to do some math on this. So keep this pictured in your notes, and we're just going to write out some quick equations for this, okay? And one of the equations is, I'm going to call this point Vx. And so I'm going to say I1 is equal to Vn minus Vx over R1. Another quick equation, we also know that this should be I1 because this is an infinite resistance. The current can't go anywhere else. So I1 is also equal to Vx minus Vout over Rf. Let's start there. And we have one other equation that I'm going to write over here, which is Vout is equal to AV0 times a negative, I'm running off, times a negative Vx. What's that? That's just saying this voltage here is negative Vx, which was over here, times that. So we're going to start with those three equations. Let's start with the easy one. We'll tie those two together. We'll just make them equal to each other. Vn minus Vx over R1 is equal to Vx minus V0 over Rf. That seems simple enough, and what we want to get with this, where we want to eventually get to this, is we want Vout over Vn. That's going to be our gain for the entire system. And there's a problem here. I have Vx, Vin, and Vout, but luckily over here, that's off the page, is I have Vout is equal to AV0 times negative Vx. I'm going to solve that, by the way. Vx is equal to minus AV0, 1 over AV0 times V0, or Vout. Okay? And I'm going to plug that into here wherever Vx occurs. Vin minus, in this case it's going to be plus 1 over a V0 times V0 is equal to minus 1 over a V0, V0 minus V0 over RF. And we have a whole bunch of V0s for this entire thing. So sorry, we're going to go, I'm going to solve this up here. And what we want to get, we're going to get V0 all by itself. I'm going to roll all the V0s to the left-hand side. V0, 1 over, and I'm 1 over here. Let me do one more step before I do that. I forgot over R1. I'm going to multiply both sides by RF over R1. Okay? And then we're going to pull all of this over to where we're at before. I'm going to pull all the V0s to the left-hand side. V0 times RF over R1 a V0 plus 1, that's this one, plus 1 over A0. And all the units make sense on this because they're all just straight gains. Ohms, ohms, volts, volts, nothing, volts, volts. This is equal to, now on the other side, we're going to have, and I know this seemed like a long ways around for this, minus RF over R1 times Vn. Okay? So far, I hope you're following along with me. And let me put this just right up here. Equals minus RF over R1 times Vn. I think we're done with all this stuff. Unless I made a mistake, then we're done with this. So we see something familiar here, and that makes a lot of sense. In fact, if you think about it right now, if we made A0 infinite, which is what we said, V out over Vn is equal to minus RF over R1. These two crank off to infinity, which makes this and this crank off to 0. Remember, soldier boys are cranking. And that brings us all the way to just V out is equal to minus RF over R1 times V in. But we're going to solve this just a little bit more nicely than this. V out over V in. I'm gonna put this into a slightly different format, and what we get is RF plus R1A V0 plus R1 over A0 is equal to minus RF over R1. And let me see. RF, R1. Oh, and there's an R1 in the denominator here. Is that right? We'll get there. Okay, V out. I feel like I made a mistake here. So A0. All I did is I found common denominators. There's an R1 down here. Okay. Multiplied everything so they all had R1, A0. And what's kind of nice about that, watch. Those both vanish. Okay. We get V out over V in. I'm going to invert this, flop to the other side. Minus RF times A0 over R1 plus R1 A0 plus RF. And let me rearrange just a little bit, plus R1. And if you look at this carefully, what ends up happening, when these two guys go to infinity, they'll eventually cancel, and this becomes insignificant. And that's what happens. When this is up at 10 to the 6th, and RF and R1 are times 10 to the 4th, okay? And then these are times 10 to the 4th, so they make those bigger as well. So these are times 10 to the 6th bigger. These vanish. And so if you have a crappy op amp with poor gain, this isn't the assumption that these two are big doesn't happen. You have to include these in here. We're going to do this in the lab. Okay? And so we end up with this as our equation. I just want you to, this is one that we should probably remember. Okay? Is to remember that gain just as it is. Okay? V out over V in is equal to minus RF A0 over R1 A0 plus RF R1. Now, I'm going to go off the rails, and you're not going to like it, but we have to do it. Next semester, you're going to take a class called Feedback Controls. We're going to do things symbolically. That's a summation. That's a transfer function. Okay? And so if we just did this, so this is a transfer function, h of s. Okay? And then we have v in of s, v out of s. And we could just say v out of s is equal to h of s times v in of s if everything is linear. Okay? And you should be doing this right now in signals and systems. This should make really, this could be a filter, it could be a system. As long as it's linear, we plug it through and we get a straight equation like this. It just goes straight through. It doesn't work in time quite as well, but let's modify this slightly. I'm also going to take the output from this. I'm going to add a new block here called a summation. I'm going to take the minus side of that and the plus side of that. And so what this looks like right here is going to be V out of S minus V out of S plus V in of S. And the problem they have is V out of S is equal to, well, itself, V out of S negative plus V in of S times H of S. And so we end up with what's a feedback problem. And we've done this before. It's called a loop equation. Okay, so this is not this is just a loop equation. If you do not have the negative here, you end up with what's called positive feedback. This is negative feedback. And this, so when we start talking about negative feedback, you should say, "Oh, crap! Negative feedback is what we did with the op amp." That's kind of interesting. We have a plus and a minus, and it goes through the amplifier and comes back. Okay, and this one, for example, we called a non-inverting op amp. Okay, but it has the same kind of things. Now, once upon a time, somebody figured this out. Okay, they did what's called collapsing the equation, and what they said is that we have to take the forward path. If we collapse this, if we want to collapse this down to G of S, and we can, that's what's cool, as long as it's linear. V in of S, V out of S. There's got to be a G of S that encompasses this entire thing. Is there, in other words, can we put that in a black box and treat it this way? And the answer is yes. Okay? And what they did is they said we have to take the forward path over 1 plus the loop path plus, because we have a negative sign here. If you have a positive sign here, you have to do 1 minus the loop path. So it's kind of a weird thing, but one or the other of these has to be negative. Well, what's the forward path? In this case, to get the forward path, we're going to break the loop path. So the forward path in this case is just H of S. There's also the loop path. So I'm going to put this back the way it was. The loop path means that we break it here and we measure the output here. And so that's just going to be, in this particular case, H of S as well. Okay? But let's make it more interesting. We'll call this N of S. So H of S times N of S. Okay? And so what would we have to do? So we'd say that the closed loop path is h of s over 1 plus h of s n of s. And we can just replace it for a block. That's what we want to do with an op-amp. So this is the same thing that we just did to solve the previous op-amp problem. Is we have to go through, and I'm going to draw it this way now. And we want the forward path over 1 plus the loop path. So forward path on this, V in, V out. Forward path, remember, I had to break the loop. And the way that we break the loop here is I'm going to disconnect this, and I cannot leave a dangling participle. Can't leave the dangling resistor. So we're going to ground it. And if you're paying attention, these two, R1 and RF, create a very nice voltage divider, and then we have A0 that's our gain in here, and it's a minus. So our forward path on this, first of all, minus A0, because that's what's inside of there. Okay? And then we have a voltage divider, which is going to be RF over R1 plus RF. And you might be saying, wait, what just happened here? This is a voltage divider to ground. We're looking at this point, right? Imagine that it's not connected here. What's the voltage here at that point? That's what it is, okay? And we're measuring the forward path from V in to V out. So that's forward path, okay? Loop path, let's put things back the way it was. Loop path, I have to measure back the loop. And so the way that we do this, I want to break it before we get back to that negative side. I'm going to, right here is my V out. Okay? Actually, I take that back. I did that wrong. We're going to put our resistor here. I'm going to break it in the same spot. Okay? But what I want to do is I want to measure, I think that's right. No, that's not right. When we do this, we're going to leave this, and I just lost it, but we can get this here really quickly. I think this is right. So I was right the first time. Nope, I was wrong the first time. Okay. My apologies. Okay, so we're going to put this through here. I'm going to break the feedback there. Okay? Which means this is going to become my V in. This one's ground. So that was really confusing, and that's why I always forget it. We want to go back to, this is the loop. We're going to break the loop before it comes back, but I'm going to feed the V in through anyways. So that's what I did. This is, in other words, this is part of that feedback mechanism, both of those. And so when I look at this one, the loop path, V in, so I have minus A0, and then it comes back, and I want to measure it here, not at the output. I want to measure it there. And if you look at that, that reversed the voltage divider. Okay? And here's what's going to be really cool. Forward path over 1 plus loop path. Okay. So what is that going to be? Minus A0 times RF over R1 plus RF over 1 plus 1, in this case minus A0 R1 over R1 plus RF. Make sure you can see it on there. Okay, and now we're going to do some simplification. I'm going to multiply top and bottom. I've got a minus sign inverted in here someplace, because this should be a plus. Okay, I do that every time, and it really bugs me, but that should be a plus. And the way that that comes from is forward path over 1 plus the loop path. The loop path would have gone back into the negative here. I'm fudging it. But if you look at this, I'm going to multiply top and bottom by R1 plus RF. And lo and behold, what we're going to get out of this is minus A0 times RF, that's this, over A0 times R1 plus R1 plus RF. That's the same equation that we got before. And so let's go back and make sure that we understand why that was a plus and not a minus. The main reason is because V in is being multiplied by minus 1. There. This should be plus. Okay? In other words, one of those had to be, we have to make sure that when V in goes in, it's not multiplied by -1. When it comes in, we had to do that one. So 1 plus loop path, that'll do it. Okay? And that's really cool. So now the trick is, and maybe you want to do this on your own, can you do it on a non-inverting op-amp? And here's how you're going to prove it. And in the end, okay, if we crank A0 to infinity, so there's two ways to do this. You can do it with the forward path plus 1 over loop path, or you can do it through the circuit mesh analysis method that I made. And you just start same place that I did. And this one turns out to be easier. But what you should end up with, right, is 1 plus RF over R1 should be our gain when we crank it. So our V out over V in should equal that when A0 goes to infinity. And so that's something that you can try on your own, and you're going to need it for one of the upcoming labs. So that's all I'm going to do for op-amps for this particular lecture, or this video. There will be another video for this lecture coming up.